in the figure has vertical asymptotes at 1 and at 2. Let's analyze the following limits. So let's look at what happens to f of x when x approaches 1 from the left. So you'll notice as x approaches 1 from the left, that will be a positive infinity. In part B, as x approaches 1 from the right, that's also a positive infinity. For part C, as x approaches 1, right, as x approaches this value, the red and the blue are converging on positive infinity, but we say that this limit does not exist due to that that vertical asymptote there. So as x approaches 2 from the left, okay, we get a positive infinity. As x approaches 2 from the right, looks like we get a negative infinity. And so, of course, here we would say does not exist. As you notice, when approaching from both sides, just because the blue and the red portion approach positive infinity, both of them do, doesn't mean that that limit exists. So we would say it does not exist for both of them. It's a little more clear to see in part F that, you know, you got one end, the yellow end of the graph going up, and the black end of the graph going down, and therefore they would never even have a chance of meeting, but that vertical asymptote takes care of the rest for the first part. So, okay, so let's look at this graph and analyze the following function. What you'll notice is that there's vertical asymptotes at -1 and at +2. It's got some interesting behavior there as it approaches 2 from the left and 2 from the right. They're going in opposite directions, but let's look at these limits. So as x approaches -1, right, as x approaches -1, clearly that does not exist. Right, we've got from the left is infinity, from the right is infinity. So we would say that that limit does not exist. As x approaches 1, our function is approaching 1 from both sides, and it looks like those would converge on 0. As x approaches 2 from the left, looks like our value would be negative infinity. As x approaches 2 from the right, we'd get a positive infinity. And in part C and D, clearly those don't agree, so we would say does not exist. Now let's evaluate a few limits or state that they don't exist. Okay, so let's go ahead and here algebraically what we're going to want to do is, because we don't have a graph to go off of for this from the right and from the left stuff, what we're going to do is we're going to pick an arbitrarily close number to 2 coming from the right. So we could go with something like 2.001. That would be approaching 2 from the right. And what we get is we just kind of look at the sign of what's really going on. We'd have 1 over, if we were just to do a direct substitution, we'd have 1 over 2.001 minus 2, which would be 1 over a very, very small positive number. Very small positive number. Clearly that, as you get closer, would approach infinity, right? As that number in the denominator gets to be a very small positive number, our y value, our output, would go to infinity relatively fast. Okay, let's do it again now coming from the left. So let's pick an arbitrarily close number. Let's go with 1.99, which would give us 1 over 1.99 minus 2, which would give us 1 over a very small negative number, which clearly, as we get closer and closer to 2, coming from the left, we would get negative infinity. And because these two one-sided limits in parts A and B don't agree, then this limit does not exist, right? So we see that as x approaches 2, we would consider the left-sided limit the right-sided limit, and therefore it would not exist due to the fact that those did not agree. Okay, so I could say one-sided limits were not equal and therefore does not exist. Okay, so let's evaluate the following limits or state that they do not exist. So let's use, again, what we'd call sign analysis. That's what we did on the last page. Let me write it out. We're going to do a sign analysis of the following. So let's approach -2 from the right. So a value that we could use would be potentially something like -1.9. Okay, if I use -1.9, I would get a negative number, okay, over a negative number times a positive number. Now, the value down here in the denominator is going to be a relatively small number. And so as we get closer and closer and closer to x, or to x equals -2, that number is going to get smaller and smaller and smaller. So that means we're going to be taking a negative number, which would be a number right around 4, divided by a very small negative number, which would be a positive infinity. Okay. Let's do it again in the next example here. Now coming from the left, we could use something like x is approximately -2.1. Okay, so we would get, again, a negative number on the top, which is going to approach 4 is going to approach -6, right, because that'll be close to a -2 minus 4. And then we'll get a negative number times a negative number as well, but that'll be a really small negative number. And so that number will continue to get smaller and smaller in the denominator as x gets closer and closer to -2. It'll get closer and closer to 0. So I'd have a static negative number, just a number that's coming closer and closer to -6, divided by a very small positive number, which would give me a negative infinity. And therefore, clearly, as we take that limit and consider the two one-sided limits, because they are not in agreement, we would say that this does not exist. Okay, so let's look at number 5. As we approach 4 from the right, we will get a negative number over a positive number, right? And the square will take care of that, which tells us that we'll get negative infinity as x approaches 4 from the right. Likewise, we're going to get a negative number over, again, a positive number because of that power there, which will give us negative infinity. Now, you might be saying to yourself, well, aren't all of these then going to be does not exist, whether they're infinite and both ending in the same direction or not? Technically, you could say that this limit would be negative infinity, but that, in mathematical terms, doesn't exist anyways. So that's how you go ahead and you evaluate limits using this thing called sign analysis. It's sometimes useful, sign analysis. Okay, so let's continue on and find all vertical asymptotes of the following functions. For each value, let's discuss the behavior on the left and the right, and then as well as the limit as x approaches that value. So the first thing you're going to want to do in this case is you're going to want to factor. And in factoring, we would see that f of x equals, it looks like x minus 7 and an x minus 2 over x minus 3, x minus 2. So immediately what you'll see is that you have a hole here at x equals 2, hole at x equals 2, and you have a vertical asymptote at x equals 3. Our purpose for this example is not to analyze what happens near the hole at x equals 2. It's to analyze the limit as x approaches 3 from the left and from the right. So let's do that. Limit as x approaches 3 from the left of our new function. So we'll take and find the limit as x approaches -3 of x minus 7 over x minus 3. Using sign analysis, if I picked a value for x, coming from the left, what I should get with a direct substitution would be a negative value over another negative value. Of course, that'd be a small negative value in the denominator, therefore I would get a positive infinity. So it looks like from the left I'm getting a positive infinity for our value that we're approaching. From the right, if we did the same thing, let's just change that to a plus. Okay, that would change our value to something like 3.1. We would still get a negative value on the top, but we'd get a positive value on the bottom, which means we'd get a negative infinity, which means that our limit as x approaches 3 of this thing, x minus 7 over x minus 3, does not exist. So what could this look like? Well, as x approaches 3 from the left, I think we had a positive value as x approached from the left and some kind of negative value as x approached from the right. So that could be a behavior that you might see there at that asymptote. And of course we had a hole at x equaled 2, so there might be a hole right there, right? Just to show you a little graphical representation of that. Okay, let's evaluate the following limits. For the first 3 here, I'm going to go ahead and draw a graph so we can remember what tangent looks like. Right? We got negative pi over 2, and we got pi over 2. These are our vertical asymptotes. And what our graph would look like is something like this. And it would repeat forever and ever. So as we approach pi over 2 from the left, looks like we'll get positive infinity. As we approach pi over 2 from the right, looks like we get negative infinity. Therefore, our limit does not exist. Okay, let's look at cosecant of x from the right. So looking at cosecant of x, I'm going to look at its cousin, or reciprocal function, 1 over sine, right? So I'm going to graph sine, and I'm just going to go from 0 to pi over 2, or excuse me, to pi. So this is what sine would look like from 0 to pi. So you might recall anywhere sine is 0, cosecant will have an asymptote. And anywhere sine is 1, cosecant will be 1. So our graph of cosecant from 0 to pi would look like that. So if we look at, what is happening to cosecant as it approaches 0 from the right, well, it's going to be going up to positive infinity. Let's take another look here at the secant of x as x approaches pi. So what we would want to look at instead of secant would be cosine. So let me sketch that a little better there. As it approaches pi. Okay, so I'm going to go from 0 to pi for cosine. Cosine from 0 to pi would do something like this. It'd be half of the period of cosine. Of course, the other half will go up like that. Okay, now again, just like with sine, anywhere cosine is 0, secant would have asymptotes. So the graph of secant here would look like this. So as x approaches pi, we want to look as x approaches pi from the left, and as x approaches pi from the right.